Hello, this lecture is about open and closed sets. We have an normed space. First definition. Let us have some point, some element, and some positive number. And the open ball with center of x and radius r is a set of all points such what distance between this point and the center x is smaller than r. X is called center of the ball and r is called radius of the ball. Another very simple definition: the neighborhood of x is some open ball with center in x. So neighborhood is some open ball with center of x with some radius. Today we will have a lot of definition. So next one, let x some element in A. So we have some set A in x, and x is called inner point for A is if there is a neighborhood of x what belongs to A. So point what belongs to set with some neighborhood is called inner point. And the set A is called open if it consists only of inner points. So for each x what belongs to A, we can find the neighborhood what also belongs to A. So such sets are called open. Set A is called closed if complement of A is open. So we say what A is closed is if its complement is open. I forgot to add what all with space X and the empty sets are open and closed. So we just agree what these sets are open simultaneously, open and closed. Now, small example. Let's consider space of real numbers. So, and segment open, segment 0, 1, so consisting of all points what are bigger than 0 but smaller than 1, it is open because for each point in this segment we can find a small neighborhood what also belongs to this segment. So it is open. If we consider the segment what includes boundary points 0 and 1, so it's set this set, it is closed because if the complement of this point is of this set, is this set, so this beam united with this beam, and if we take any point from the complement, in this side for example, we can find a neighborhood what belongs to this complement together with the point. So this set is closed. If we consider the set what includes point 0 but doesn't include point 1, it will be neither open nor closed, because this point belongs to A, but we cannot find a neighborhood because each neighborhood will have a point from complement of A, and this point belongs to complement, but we cannot find the neighborhood what entirely belongs to neighborhood. So neither set nor its complement are open, so this set is neither open nor closed. First small theorem. Let's we have a family of open sets. Then the union of these sets is also open. If we have find second item have a finite family of open sets, then the intersection of this family is also open. So union of any family of open set is open, but intersection only for finite family. And the opposite situation for closed sets. Let's set, I don't know, F alpha is closed for each alpha. Then intersection of these sets of alpha is also closed. And if we have finite family of closed sets, and we can say the same for its union. So this is the theorem. Now let's prove it. Item number 1. Let's take a point in the union of A alpha means what it belongs to some set of this family. So if we recall what does mean union, it says what we can find a index such what x belongs to alpha 0, A alpha 0. But this set is open, so we can find the neighborhood, what also belongs to A alpha 0. And so it belongs to union. So we take arbitrary points from the union and we have found the neighborhood what also belongs to this union. So first item is finished. Item number 2. So let X belongs to intersection of a finite family of open sets. It means what X belongs to each set. So for each I from 1 to k, X belongs to A I. And each such set is open, so together with X it includes some neighborhood of X. In any set, so it's particular neighborhood. So for each I, what's from 1 to k, we can find some positive number Ri such what ball with center x and radius Ri belongs to AI. So this is neighborhood in for case number I. So let's R is a minimum of all these radii and the minimum of finite number of positive numbers is also positive. So a ball with center of x and radius R belongs to all previous balls. So this neighborhood belongs to all sets A alpha. So it belongs to the intersection. Second item is also finished. For next two items, we need some very useful formula. Actually, two of such formulas. The complement of union of some family of sets is equal to intersection of complements of these sets, and another formula, the complement of intersection of some sets is equal to union of complements. Let's prove this first formula, and second, I hope you can do it yourself. So let x belongs to complement of this union, then x doesn't belong to the union. Then there is no element such what x belongs to, not element of a set of indexes. What x belongs to this set. No, indeed, x belongs to union if it belongs to some set. doesn't belong if we cannot find the set such what X belongs to this set. It means what X doesn't belong to any set A alpha. And it means what X belongs to complement and X belongs to each complement means it belongs to intersection. From the other side, if X belongs to intersection, means what it belongs to each complement, so we can inverse this arrow. Belong to complement means doesn't belong to the set, so we can do the same for next implication. Then X doesn't belong to all sets means we cannot find an index such what X belongs to this set. So the same here. Doesn't belong to, we cannot find a set such what X belongs to this set means X doesn't belong to all sets or union of sets, then it belongs to complement. So these two things are equivalent, and it means what a point belongs to these sets if and only if it belongs to this one. Sets are equal. So this formula is proved. And using this formula, it is very easy to prove item 3. So, if we consider an intersection of closed sets, we have to prove what it is closed, and we do it if we prove what its complement is open. So, according to this formula number B, it is union of complements open. Union is also open according to first item, and that's it. So complement is open, so this set is closed. Number 4, please prove yourself. So this theorem is proved, and we continue. Another definition is about limit point. Set point X is called limit point of set set A if any neighborhood of X has a non-empty intersection with A. So in any neighborhood of X, there is a point E from A. Now, immediately from this definition, it follows what all points from A are limit points. So if X belongs to A, then X is a limit point of A. But other implication doesn't happen all the time. And about this, the next theorem. Set A is closed if and only if it contains all limit points. So if X limit point of A, X belongs to A. So closed set A contain all limit points. So let's prove this theorem. Let's A is closed and let X is a limit point. So we prove this implication. Let's assume contradiction. Let's assume what X doesn't belong to A. So X belongs to complement of A, and since A is closed, its complement is open. So we can find a neighborhood of X what also belongs to complement. But if this neighborhood belongs to complement, it doesn't intersect with A because it is included in the complement. And if it doesn't intersect with A, it means what X is not a limit point. Because for limit points, all neighborhoods intersect with A. So we have a classical contradiction: X is limit point, X is not a limit point. So our assumption that X doesn't belong to A is wrong, and X belongs to A. Opposite. We have this, and we need to prove what A is closed. To do so, we need to consider its complement. So take arbitrary points from the complement and find a neighborhood what belongs to this complement. Once again, let's assume the contradiction. Let's assume what we cannot find such complement, such neighborhood. It means what all neighborhoods have non-empty intersection with A. It means what X is a limit point of A, because this property is fulfilled only for limit points. And according to our assumption, X belongs to A. But we took point from the complement. So once again, we have a contradiction. And it means what there is a neighborhood what entirely belongs to complement of A, and so complement of A is open. So this theorem is also proved, and that's all for now.